Okay, so today we're going to be talking about sound. Sound is one of the most, or it is kind of the most, indicative, or quintessential type of, longitudinal waves, where instead of going up and down physically, the medium that, carries the wave, has differences in pressure, where there will be high pressure and low pressure sections of the wave, and then the wave is going to be carried around uh, by changes in pressure, where delta P equals delta P max sine kx minus omega t plus phi. Or alternatively, you can use the uh, formulation that instead of changes in pressure uh, from the original state, you can have change in the distance between the molecules. Delta S equals delta S max sine kx minus omega t plus phi. Where if you graph either of these, delta p or delta s, it's just going to look like, uh let's say, at t equals 0, we're graphing it like this. Then both of these are still just going to look like sine waves if we graph delta p or delta s, even though, unlike if we have y here, this is not actually going to be moving up and down. It's just going to be a change in pressure, or a change in the distance between the molecules. So that's the main uh thing to talk about. That's going to be like our intro to sound, just saying that it's a longitudinal wave. And in the same way that in a very similar fashion to how we derived the velocities last time, we have v equals the square root of the bulk modulus over rho, or v equals the square root of Young's modulus over rho. Uh, and where the bulk modulus is for fluids, the Young's modulus is for solids. And then we also have the equation that V equals gamma R TK over M, where this is going to make more sense in the next semester. Gamma is a constant, R is a constant that converts uh, temperature to energy per mole. And then M, I believe, is the number of moles. And then at sea level, this is going to be equal to 331 meters per second times the temperature in Kelvin over 273 Kelvin. So yeah, I'm not going to bother deriving those because it is very similar derivations to how we derive the relationship between velocity and tension. But those are going to be the velocities that you're going to see for uh, yeah, the velocities you're going to see when you're talking about sound. And I think at room temperature, the temperature we're at 20 degrees Celsius the at sea level is going to be 334 meters per second, so that's usually going to be the value that we're going to use. So I'll just write that down. And then, yeah, that's all I have to say about that. I'll come back with more just quickly going through more specific versions of these questions or the next sections.